you can observe here, the principal stresses are related with the material property, which is yield in tension. Okay, so this is regarding maximum principal strain theory, and the last but one will be maximum strain energy theory. For this maximum strain energy theory, there is no need for any derivation. You just try to remember it, which will be sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2, which is equal to sigma yt by factor of safety whole square. Now, what is strain energy theory? For basic understanding maximum strain energy theory, that means strain energy is nothing but the energy stored in the body up to proportionality limit due to change in its shape. For example, just try to compress a spring. What happens? The spring, when you release the spring from compression, when you release the force on the spring, it tries to expand and comes to its original position. Now, where do the spring gets energy? Where do the spring gets energy? As thermodynamics first class says that energy can neither be destroyed neither be created. That means energy is just converting from one form to another form. That is, the energy that you have applied on the spring is converted into strain energy. That is, the energy that is formed due to change in the shape of the spring. Okay, so the energy is stored in the spring, and that energy which is making the spring to come to its original position, we call it as strain energy. It's not only spring, it can be of any material which is elastic in nature. Okay, there is no rigid material in the nature. It's every material will be having some strain energy when you apply a load on it due to change in its shape. Now, when the strain energy that is developed in the body exceeds the yield strength in this tensile specimen that is used in the lab, then the failure for that particular component occurs according to this particular total strain energy theory. Now, the last one, which is most important one, that is distortion energy theory. Now, what does distortion energy theory says? It's a very important theory, because as I said, strain energy is a whole form of energy that is stored in the body. But strain energy can be divided into two types. One is the energy that is due to the volume, change in the volume and change in the shape. As a mechanical engineer, for example, if you take a rim of a bicycle or a rim of an automobile or a two-wheelers, so what happens when the shape of a rim changes, or the shape of the rim gets distorted? The whole purpose of the rim gets distorted. That is, you can't use that particular rim, right? It induces some vibrations in it. So for that particular sense, the strain energy is divided into two types. That is, the strain energy that is developed due to change in the volume, and the strain energy that is developed due to change in the shape. So we call it as shape distortion, and von Mises theory deals exactly with the shape distortion, which is much more important in mechanical applications, where shape itself defines the application of a particular machining component. Example is your automobile rim, which induces force when the circular shape of the rim is distorted. Now, what is the governing equation? Here it will be sigma yt by factor of safety whole square is equal to sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square. Okay, so it will be the governing equation for distortion energy theory. Now, when someone asks you why you have gone for von Mises theory, or else what is distortion energy, you can say like this. So the strain energy that is developed in the body can be divided into two parts. That is volume energy, the energy that is developed due to change in the volume, and the energy that is developed to change in the shape. Now, when it comes to change in the shape, when it comes to change in the volume, first of all, there won't be any change in shape, right? When volume gets changed equally. Okay, then but when you go for change in the shape, the whole purpose of serving will be change, or else it won't be again used. Okay, so for that purpose, the change in the shape must be considered seriously, and that's what von Mises theory deals about. And it gives a relation between that particular distortion energy, that is the energy that is developed due to change in the shape, to the material property, that is sigma yt, that is yield in tension by factor of safety. Okay, I think with this you got a clear idea regarding the theories of failures. theory regarding the forces that are acting on a body, what is uniaxial loading and what is multi-axial loading. Okay, so I'm erasing this. So we solved a number of problems on this series of failures. Just go through this lecture and parallelly take your tutorial notes and try to don't solve, try to see the methodology that is involved in solving these particular problems and then go for solving the problems. If you want any extra problems, go for textbooks like V.B. Bhandari, Shigley. Okay? Yeah, I have completed theories of failures, and the next a small theory, that is stress concentration. Stress concentration. Okay, now consider this paper as a mechanical or as a machine element which is having a hole in it. Now apply a tensile force in this direction. Now see where does it will fail. See, now it is getting failed exactly at the position where it is having hole, right? Now that means you can say, you can infer here that the stress that is acting at this whole portion is more when compared to the stress acting at the solid portion. So with this small demonstration, you can easily gain knowledge that the stress is getting concentrated at that particular point where you are having a discontinuity in your particular dimension, that is in your area. Okay, so when I apply force like this, now the failure occurs at this particular point. That means the entire stress is concentrated at this particular point, which we call it as stress concentration. Stress concentration is nothing but it's a localization of stresses at a single point due to abrupt change in the cross section or as the properties of the material. We call it as stress concentration. Now what are the effects of stress concentration? As I showed you, when you take a component with a hole in it and you apply a tensile force, you can observe a crack exactly at the portion where you are having that particular hole. The best example for this is your bolt that are using in your daily life, where you will be having bolts, or else if you take a shaft, you have to make a keyhole for it. You have to make a keyhole for it in order to fit a key here. Okay, so what happens here, when you make a hole here, there is a change in the cross section, right? There is an abrupt change in the cross section, because when it is rotating, okay, when it is rotating, the stress that is acting at the outer parts will be more because there is discontinuity in cross section, that is material here, which will rise to severe stress concentration, and you can observe cracks developing in this direction. Okay, so bolts are best example for this, because you will be having, for bolts you can see threaded section of the bolt which is having a change in the cross section, okay, which results in stress concentration, heavy stress concentration. Okay,
this video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.
now the normal stress that is calculated using the formulas, it will not give suitable solution or else a safe dimension for stress concentration. So for that you have to find, for that you have to use some special factor which is called stress concentration factor, which is represented as K suffix T, which indicates that as stress concentration factor theoretical. So theoretical stress concentration, which will be maximum stress by theoretical stress. So theoretical stress is nothing but the stress you have found using your formulas, and maximum stress is that the stress that is developed with the stress concentration, and Kt, that is stress concentration, that is theoretical stress concentration, where you can find it using your data book depending upon the type of the machine element and type of the loading. Okay, type of the loading. This is regarding a small introduction regarding stress concentration. You can see this effect of stress concentration in fatigue loading, where you will be getting the fatigue stress loading concentration factor, that is Kd, which is equal to 1 by Kf, where Kf will be indirectly will be dependent upon the Kt with Q, that is notch sensitivity. Okay, this is the first part in CO1. Now the second part in CO1 deals with the fatigue loading. Now up to now, the loads that are acting, we have seen, are static in nature, that is the magnitude and the direction of the loads are not changing. Okay, but when you go for fatigue loading, the magnitude as well as the direction of the load gets changed. For example, if I take a shaft which is rotating, okay, it might go through a stress which will be ranging from minus 50 megapascals to plus 50 megapascals, so which is subjected to a compressive stress and a tensile stress for every cycle, that is it is repeating, the stress gets repeated. Okay, so what is happening here, the stress is not remaining same, the magnitude as well as the direction. Okay, we call it as fatigue loading, where the stress is acting in the form of cycles, where it will be changing in both in magnitude and direction. Now you can think in such a way that due to fatigue loading, as the magnitude is changing for different types of cycles, for different cycles the magnitude of load is changing. As the load is changing, the failure for a component might occur much before than the sigma y, that is the yield. Okay, the failure of the component might occur much more than the yield stress of that particular component. Okay, so this is a bad sign for a mechanical engineer, because you can't predict the failure of a fatigue loading. So sometimes it might go beyond yield stress, and sometimes it might failure even without reaching the yield stress. Now for that purpose, we have another factor called endurance limit. Okay, so what does endurance limit gives us? Endurance limit is nothing but the number of cycles. Endurance limit gives us the number of cycles that a specimen in a rotating beam has gone through before the appearance of the first crack. Okay, that means the stress that is developed before the appearance of the first crack, okay, before the appearance of the first crack in a rotating beam specimen. Now what is rotating beam experiment? Just as like your universal testing machine, that is UTM, for torsion, for fatigue loading, we have rotating beam specimen, in which the specimen is loaded and it will be subjected to completely reverse loading. Now what is meant by completely reverse loading? When you are, as I said, that fatigue loading is not constant, that means the load will be changing for each and every cycle. If the load changes in such a way that the maximum and minimum are same, that means sigma max is equal to plus 50 megapascals and sigma minimum is equal to minus 50 megapascals. That means only magnitude is changing, but only magnitude is remaining same, but the direction is changing here, so which we call it as completely reverse load. The load is reversing completely such that the magnitude remains same but direction will be changing. Okay, so this is completely reversed load, and endurance limit is the limit that we will be taking for the design in fatigue loading, which will be around point, sometimes it will be 0.5 times of sigma YT, sometimes it will be 0.8 times of sigma UT. You can't expect that it will be given in the questions itself, or else some standard parameters were used from manufacturers catalog for different materials. Okay, so fatigue loading, we are discussing regarding fatigue loading, and fatigue loading in the sense the load is not constant, just like static loading it is not constant, and the load is changing for every cycle. For example, if you take a load that is required to break a copper wire that is used for electrical purposes, the electrician will apply force in upward direction and downward direction to break that particular copper wire. Now what is happening in that particular case to break the copper wire? So the electrician particularly applying force in one direction, that is in tensile direction and in compressive direction. That means the force is applied in the form of cycles, and its magnitude and direction is changing for each and every cycle. So that type of force we call it as fatigue force or fatigue loading. Now you can observe that in fatigue loading, the failure of the object or particular mechanical element is not predictable. Actually it's unpredictable. It may fail before the yield point also. For that purpose, we don't consider yield strength for the material directly in the design for fatigue loading. We will be considering endurance limit as the limit for design for a fatigue loading. Okay, so we will be looking in different fatigue loadings, because fatigue loading is also of two types actually. So we will be looking those things. So if the first load is, if the magnitude of load remains same but the direction changes. Example, you can quote it like this. Example, the load varies from plus or minus 50 newtons. So you can say that the direction of load is changing but not the magnitude. Okay. Now the second type is both direction and magnitude are changing at a time. Both magnitude and direction will be changing. Example, so it will be plus 50 newtons to minus 30 newtons. So the load is applied from tensile to 50 newtons to in compressive 30 newtons. That is, the load is changing for every cycle, and this type of load we call it as completely reverse stress, and this type of load we call it as alternating stress. We have to keep this in mind that we will be having two types of stresses, that is completely reverse stress and alternating stress, depending upon the nature of the load in fatigue loading. So if he gives you the load with the same magnitude but change in direction, you have to go for the analysis of completely reverse stress. And if he gives you both the change of both direction and magnitude, then you have to go for alternating stresses, analysis using alternating stresses. Now we will be discussing the analysis using completely. So what are the steps that are to be followed in completely reverse stresses and in alternating stress? Okay. So when it comes to completely reverse stress, as I told you, so there is rotating beam specimen test where it is used to find the endurance limit of a particular mechanical machine element. For example, it's a shaft, because it will be rotating and it will be subjected to completely reverse stresses. Okay. So you know that in an uniaxial tensile test, that is in UTM, universal testing machine, So we will be plotting T delta curve or else stress strain curve. Okay, so in the same sense, by using rotating beam specimen test, we will be plotting a curve called SN curve. We use it as SN curve. This is the y-axis, that is the ordinate will be S and abscissa will be N, which is N will be number of cycles and S will be endurance limit. So that means for a particular endurance limit, you will be finding number of cycles, and usually it starts from 10 cube, 10 to the power of 5, but as the values are very large, we will take it as log plot. We will be going for log plot, log plot. So it will be 3, 4, 5, 6, 7, 8, which are nothing but.
This video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.
You know, it's 10 to the power 3, 10 to the power 2, 10 to the power of 4, 10 to the power of 5. So there is special significance why it starts from 3 actually. So before 3, that means for 10 to the power of 2, 10 to the power of 1, it doesn't consider as fatigue loading because the number of cycles were very less. Okay, so only after 10 cube cycles, or else when the number of cycles are equal to or greater than 10 to the power of 3, then only it is considered as fatigue loading. And for mild steel, so it looks like this. So up to 10 to the power of 6, so it will be, the curve will be, you know, the load will be linear, and after that it will be asymptotic. Asymptotic in the sense, so it will be parallel to the x-axis. Okay, asymptotic in the sense it might be parallel to any one of those axes. So and it is linear. So the particular load, we call it here as endurance limit, that is the limit of that particular element. Okay, and this is the maximum limit and this is the minimum endurance limit. So when you design a particular element, machine element, I told you in the first itself, for a fatigue loading, you have to design it for what type of load? You have to design it for endurance limit, not for your material property directly. As I told, fatigue loading might fail your particular component before yielding itself. So you don't, consider yielding as a criteria for failure. So you have to consider endurance limit as your criteria when you go for, fatigue loading. So for that purpose, your designed endurance limit must exist between these 2 points. Then only your particular machine component will be of safe region, will be in the same region, safe region for that particular number of cycles. So it will be having these many number of cycles for this particular endurance limit, or else vice versa. If you are subject to this particular cycles, your element will be subjected to this much of endurance limit. So we will limit our discussion on SN curve up to here, because the main purpose of SN curve is to just understand how it is built, okay, how it must be used in order to find the number of cycles for a particular element. So how can you find this? Just by knowing endurance limit of a particular element, you can find the number of cycles, because on y-axis you are having endurance limit, on x-axis you are having number of cycles. Okay, endurance limit. But the thing you have to understand here is, you can't use the endurance limit of a particular element that is used practically directly, because the results that obtained using a specimen and the results that are obtained in a particular in a practical sense will be different, because there will be a lot of derating factors which are to be considered. So the endurance limit for a particular element which is to be applied practically, it will be derating. We call it as derating factors because it derates the endurance limit. So it is, we call it as SC, which is equal to KA, KB, KC into SE dash. KC is reliability factor, shape factor, size factor and reliability factor, which are constants, and will be given in your question. So you have to consider those factors and you will be solving this particular problem. And we will be having one more factor, which is KD, K suffix D, which will be, so KD, which is nothing but dynamic fatigue stress concentration factor. We call it as fatigue stress concentration factor. So how will you find KD is equal to 1 by K suffix F, where Kf can be found by using KT, 1 plus Q into KT minus 1. Q we call it as notch sensitivity, notch sensitivity. Okay. So now SE dash will be the endurance limit of that particular mechanical specimen which is used in labs. So and Ka, Kb, Kc, Kd were shape factors, size factors, reliability factors and fatigue loading stress concentration factor. Now Q, for finding Kd you have to find K suffix F, which is equal to 1 plus Q into Kt minus 1, where Q is called notch sensitivity and Kt, as we discussed, it's nothing but theoretical stress concentration factor, which can be found from your data book, page number 7.11. So you will be having different graphs for particular stress concentration factors depending upon the type of the load and type of the mechanical element. For example, if you take a shaft subjected to bending moment, you will be having a different graph. So in the same way, plate with a hole subjected to a tensile load, you will be having a different graph. So depending upon the D by D ratio, you will be finding the KT value. Okay. Now it's notch sensitivity. It's a very much interesting topic. Now what is notch sensitivity? Notch sensitivity is nothing but the same plate with a hole is when it is subjected to fatigue loading. What happens? So it's different when it is subjected to static and when it is subjected to fatigue. So it's the ability or else it's the nature of the particular plate when it is subjected to notch or else when it is subjected to hole, when it is having hole or notch, when it is subject to fatigue loading. Okay, the ability to withstand or succumb, the ability to succumb that particular fatigue loading, we call it as notch sensitivity. So and it will be of less than 1, value is less than 1, which will be 0.5 to 0.9. Okay, it will be 0.9. So Kf is equal to 1 plus Q into Kt minus 1. Okay. So this is under reverse axial loading. This is completely reverse axial loading. Okay. Now the only thing that is left is alternating stresses. Whenever he asks you to find using reverse axial loading, you have to either use this particular formula and you have to find endurance limit. From endurance limit we will be finding the stress or else the area that is required for a plate to thickness or width of a plate that can withstand that particular fatigue loading. If he asks you to find the number of cycles or else number of life cycles, then you have to use SN curve. So this particular concept will be used when the life is infinity. So when the life is infinity, that means when the life of a particular machine component is infinity, we will be using certain direct rules or direct thumb rules where you can find that endurance, that is stress, axial stress is equal to 0.8 times of endurance limit. That means corrected endurance limit, 0.8 times of endurance limit. You can take it directly and you know that stress is equal to P by A. If you have factor of safety, include factor of safety here. Now if you take bending load, sigma B is equal to 1 into SE by factor of safety. That means there won't be any load factor here. We call it as load factor. Okay, K suffix L. We can take it as a K suffix L. In question he might give it as a load factor. That means when a question is given on infinite number of cycles. That means if he doesn't mention anything regarding the number of cycles or the life of the particular machine component, you have to use this particular method to solve a problem in order to find the area of a particular machine element. If he gives you, or else if he asks you to find the number of cycles basing upon the endurance limit, the first step will be common, that is finding corrected endurance limit. Use this corrected endurance limit as y-axis and plot the graph and find this the life that it can sustain for this particular corrected endurance value. Okay, and this will be you can use this concept, you can find by using a similar triangle concept, or else you can interpolate it directly. Interpolation is nothing but it's a linear equation which can be found by y equal to mx, line, y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. It's a straight line equation. From that you can find the unknown that is in the equation. Okay, so that is for reversed axial loading, in which we will be having two cases. First one is infinite number of cycles and second one is finite number of cycles. We use SN curve only when it is finite number of cycles. Now the next topic is alternating stresses. The next topic will be alternating stresses, that is alternating stresses. That means both magnitude and direction will change. You can't guarantee that magnitude will remain same, but magnitude will change, or else its direction will also change. For example, it might be from plus 50 to plus 30 also. It might from plus 30 to minus 110 also. So you can't guarantee that both magnitude and direction will change. But the thing is, its magnitude will change for definitely. The direction might change or might not change. Okay. So if you draw a diagram for this alternating stresses, considering that both are in a particular positive limit, that is both are in the same plane, that is in the first quadrant, I can get a curve like this. Okay, so if it's of a completely reversed stress, so it looks like this. So that means the maximum load here will be the load, the magnitude of the load at this point and this point will be same, but the nature of load will be changing. That is, here it will be plus and here it will be minus. Okay, so we have two components to find here, that is, those are sigma mean and sigma amplitude. We call it as mean stress and this one as amplitude stress. Now what is mean stress? Mean stress is nothing but sigma m is equal to sigma max plus sigma minimum by 2. Okay. Now what is amplitude? Amplitude stress is equal to sigma max minus sigma minimum by 2. Okay. So now just consider in such a fashion that if it's if it's a reversed axial stress, that both sigma max and sigma minimum will be equal in magnitude, but it will be changing its direction. That means sigma minimum will be minus of sigma maximum. Now if I substitute this, what happens? Sigma m tends to 0. That means mean stress will be 0 in what? Reversed axial loading. That means reversed loading, completely reversed loading. Now what happens to sigma a here? Sigma a is equal to sigma max minus sigma max, which will be 2 times of sigma max. When 2 and 2 gets cancelled, only sigma max will be available for design purpose. So when you design for a reversed axial loading, you will be designing for directly as sigma max, that is amplitude stress is equal to maximum stress. So as its mean stress is 0, the effect of there won't be any effect of mean stress, but its amplitude stress, the effect of the amplitude stress is nothing but it's equal to maximum stress, that is developed due to maximum load. Okay. So now this is the basic concept that is required for alternating stresses, because it might not affect for the completely reverse loading, but it affect for alternating loads. It might affect for alternating loads. Now what happens here in alternating loads? It can't be 0. Sigma m, that is mean stress, can't be 0. So if sigma m is equal to sigma max plus sigma minimum by 2. So sigma minimum can't be 0. That is, sigma minimum is not equal to sigma max here. So that's why the value of sigma m remains greater than 0. So in the same way, sigma a is equal to sigma max minus sigma minimum by 2. Okay, that means both the values exist in alternating stresses. So that means you have to design your particular machine component in such a way that you have to consider both amplitude stresses and mean stresses. So for this particular concept, there are 3 lines, particular concepts or else theories, which are used for the design of the mechanical components subjected to fatigue loading under alternating stresses. Are there are 3 theories. First one is Soderberg theory, second one is Goodman theory, and the third one is Gerber's parabola. So out of these 3, the first 2 are there for your syllabus, and we will be discussing one by one the first 2. So we can show the plots in the same graph. Actually, you can superimpose this in the same graph. So it will be sigma a will be on y-axis and sigma m will be on x-axis. So Soderberg line will join amplitude stress to yield stress in tensile, that is sigma yt, and Goodman line will be drawn between endurance limit and ultimate tensile stress, and Gerber parabola also will be drawn between endurance limit and sigma ut. Okay, that is ultimate tensile strength. Now by seeing this graph, we can formulate the equations, intercept equations. Now what is the intercept equation? X by a, line intercept equation, x by a plus y by b is equal to 1. Okay, for Soderberg line, so what is x and y axis are common for Soderberg and Goodman, right? Now what is x axis? Sigma.
For more updates, stay tuned to KL Radio, the voice of Kalians. This video is brought to you by Monster 6, co-sponsored by TechnoSpark.